I wanted to do a video to show what goes into saving some of these motors. The majority of motors that come to me just need simple repairs. Sometimes they're just frozen up, need the spacers replaced, a good cleaning, and that's why I don't charge a whole lot. But sometimes I get motors like this one. This is a motor usually referred to as a FAT, and is found in the Model 17s and all the other 170 somethings. They go back to from 48 and used up into the 80s. So often it's hard to tell how old these motors are. And when I got this one, the motor turned freely, and so I was pretty hopeful. But once I opened it up, I realized this motor had been abused heavily. We look at this picture, and you can see how dark the wiring is, and it's definitely been overheated. I didn't realize how overheated it was, so I took it apart further. On this one, you can see where the wires from the armature fields come up and connect to the commutator, and most of them are burned off. They're not connected at all, and if you look at that commutator, it looks like it's just been really roughly used. And on this picture, you can see the commutator is actually melted. Now, my suspicion is that someone accidentally hooked this up to 110 instead of 12 volts. I don't think 12 volts would have melted that copper. And when I saw that, my first thought was, there's no repairing this motor. It's just shot, which is a shame. I hate to see a motor not be able to be repaired. But I thought about it that night, and I thought, well, maybe, what if I could rebuild that commutator? And I've never done that before, so I did some research and looked on YouTube, and I found an idea on how to do it. So the next day, I got a piece of 1/4-inch round copper tubing, and I hammered the end of it flat. And I went by the thickness that I needed it to be. I measured it as I hammered. Didn't worry about the width. I needed to get the thickness. And once I got it hammered down, I cut off the end of it, and I have this piece that you see here. Now the piece on the right is the one that came out. It's melted, it's tapered. The top part is the width that I need. So I used my Dremel to sand it down, to file it and shape it. And I got it to where it would fit into the space on the commutator. And I wasn't worried about the length very much, because where most of the plates on the commutator have a tab that bends up and locks the wire into place, I wasn't going to try to make that on here, because this copper is kind of weak, and I think if I bend it to try and lock the wire down, it would just break off. So I decided to leave it a little long, and I would just use it to solder the wire. After I got it shaped the way I wanted to and to fit into that space, I had to glue it down, and so I used some JB Weld to seat it in there. And then I put the armature in a drill, and using some sandpaper, I spun the armature around, contacting the commutator, and shaped it back down, polished it back up, made sure everything was smooth. I couldn't have the edges of this sticking up, because that would just damage the brushes. It has to be smooth, so that when I spun it with my fingers, I wouldn't feel a difference between the one I added and what was already there. And it took a little while, but I got it shaped up. Then I completely stripped the armature, taking all the old wire off, and got it prepped for rewiring. Now, prepping this for soldering, first thing I had to do, and I missed the camera on this, is I had to clean the copper parts off with acetone so that it would accept the solder. This is, you're going to use 26 gauge wire, which is what came off of it, 26 magnetic wire. I clean the end of that off so that it can accept solder. Got to get all of that lacquer coating off of it, the insulating coating. And I didn't cut this section up because I wanted you to see the reality. I'm not a master solderer, so this is not always a quick dab and go on to the next thing. Soldering can be funny sometimes. Your soldering iron will melt solder, and you melt it onto the copper plate, and then you need to tin the wire, which means put a little light coating of solder on the wire so that when you put the two together, the two surfaces of copper bond each other. Now, when you have solder already on and it's cold, a dry soldering iron will not melt it. You have to put a little dab of solder on the soldering iron in order for it to melt the other solder. I can't tell you the science behind it, but that's how it works. And that's what I was doing there. I was putting a little dab on there and getting it in there. My big fat hand's in the way. I don't have a way to position this camera where I work to give a good view. That's something I have to work on in the future. The wire did not stick the first time, so I'm trying it again. And now it's stuck good. To make sure I don't want it to pull off easy, so I'll give it a good tug. So now that I have the wire attached, it's time to wrap it and start winding the fields. This motor, I believe, has 10 fields, so there's going to be 10 windings, and this one uses 30 loops of this 26 gauge wire, so that's a lot of winding. And I also have to insert those little blue pieces of cardboard down there. Those are to insulate the armature. The armature has to be insulated from the wire, or the wire will short out through the metal. So those are in place, and they're open on the ends. And the first loops are a little difficult because you've got to get them to go in that little slot. Now, as you add wire, the slots open up a little bit as you're putting pressure on it, and it makes it easier as you go. But it starts off a little slow. And again, my hands are in the way. It's hard to see how this is done. I'm going to speed this up because there's no point in here watching me do this for 30 loops. Now, after my third loop, I have to see where the wire is going to attach to the next plate, and I have to clean off the insulation from the wire so that it will accept the solder. And then I'm going to solder that in to the proper commutator plate. And you'll see me struggle a bit with the solder here too. It took me a couple of dabs to get it to stick. And I only have to do this 10 times. So it's a time consuming. I can only do 1 or 2 fields at a time because it really cramps your hand up holding that thing and then winding that wire. Doesn't help that I have carpal tunnel in both hands, so it takes me a while. So this was actually about a 2-day process of winding all these fields. This wire does not want to lay flat, and that makes it difficult. And I'm trying to use as little solder as I can because this area cannot stick out, and so that makes it difficult.
Ow.
Once I finally have that wire attached, I need to check it before I move on to the next one. One, to make sure that there's continuity between the 2 plates for the field, and that there's not continuity to anywhere else on the metal, showing a short or grounding anywhere. Here you see I have several of the fields done. Still working on it. And once all the fields are done, I put the armature back into the motor, reinstall the brush plate, get everything connected, close it back up, and then cross your fingers as you do a test. And I did it right the first time, got everything the way it's supposed to be, and got the clocking of the brushes to the armature fields, and the motor runs perfectly. So that gives you some idea of what goes into saving some of these motors. The simple ones, like I say, I charge very little. It's usually $25 plus return shipping. But if you have one that's going to have to be rewound or something fabricated, you can understand why I'm going to have to charge more for that. But we get motors that are dead back in the service, and these are not replaceable. You cannot get these motors anymore, so this is something I really enjoy doing, and I'm happy to get these motors back out in the service and keep these beacons and these light bars running.